this idea of a relationship between two terms or two things, right? An association, we would call it. All right, and that's what chapter 4, which is, we've gone back, that's what chapter 4 is in essence about. This correlation or association between two variables, okay? If you think back, I know we're kind of going backwards in time a little bit, but for the most part in the entire semester, we have talked about a single variable, right? We have talked about something happening to a single proportion or something happening to a single mean or a single standard deviation, okay? That's what we've looked at the entire semester. In fact, we were even talking about when we ran our confidence intervals and our hypothesis testing, we did it on a single variable, right? Okay. Well, right now what we're going to talk about is what happens if you have two variables and you want to know if there's an association between those two variables, which we do a lot, right? That would be something that you would want to think about in a lot of examples that come about. So that's what the focus of chapter 4 is about. Is there a relationship between two things? And that's specifically what we're focusing on in section 4.1. Okay. And just like before, when we started out in this semester, we talked about, graphically displaying something, right? Graphically displaying a qualitative variable with a bar graph, or graphically displaying a quantitative variable with a histogram. Here, if I have a scatter plot, this is a graphical display for the relationship between two variables. It's what you would most likely see in a traditional math class when we graph things on the X and Y axis. That's what we did. We wanted to say that was there a relationship between our independent variable along the x-axis and our dependent variable along the y-axis. And we're putting that in perspective now in statistics. This would have been something kind of like a word problem that you would have had in a traditional math class. Okay, and what we see when we talk about scatter plots, now scatter plots are a special kind of a graph in that it's just the individual ordered pair, right, for the data that we've collected. All right, which is why it's kind of a scatter plot, why I think it's called that way. And what we do is when we look at a scatter plot, we do this so that we can try to identify any trends that we might see, any relationships, and so forth, any patterns that we might find. So it is a way for us to understand the data. It's just, I'm looking at this relationship between two variables. Now, when we think about what type of a scatter plot we might see, I have several of them listed up here for you. Okay, what do you notice about the dot plots or the scatter plots on the very far left? And it tells you at the bottom of the screen, at the bottom of that image, but what type of a shape, if we call it that, do you see over there? It's linear, right? It is a line. So all of those dots on the left-hand side here, all of these dots are lined up, if you will, in a linear fashion, either in a positive or in a negative fashion, all right? And so when we have this positive direction, what we think of when we talk about a positive direction, we would have called it a positive slope. But when we think about a positive direction, what we're saying is that as one variable is increasing, the other variable is also increasing. Contrast that to a negative slope or a negative direction. And when we think of that, that's more of an inverse relationship. When one is increasing, the other is decreasing, right? So that would have a negative slope, okay? Now the other pictures that you see up here are, you can talk about them being lining up, if you will, in some sort of shape. So here we have some sort of a curve. Some of you might recognize that as being parabolic in shape or a quadratic in shape. Okay, here we have sort of a cubic function right there, or another type of a curve. And then finally, you have this one over here on the very far right, where that's not really anything, is it? Okay, it doesn't really line up as anything. It just looks like a bunch of dots on a picture. All right. But what we're going to focus on, if you'll notice, these three on the far right do not show a linear relationship. And that's what we focus on in section 4.1 is that linear relationship. Whereas, although you can see they line up, those two in the middle, they line up in some sort of fashion, that's not the one that we're going to focus on. Okay. Now we're going to talk about the strength of our relationship a little bit more in detail, but this is where there's a little bit of wiggle room in how you want to describe it. The strength is somewhat subjective. Most of the time, if you have your dots all lining up and they look really pretty and they're really kind of close to a most definite tight line or figure, you would say that that has a strong relationship between the two variables that we're comparing. Okay, and as your dots start to disperse and as the image, let's say, just kind of falls apart, the strength of that relationship changes in its identifiers. So as it's kind of falling apart, we could say it has a moderate relationship, or when there's no distinct picture, we might say it has no relationship. And again, those modifiers right there for strong, moderate, that kind of stuff, that's somewhat subjective depending on what you're looking at. And then finally, when we're looking at scatter plots, some people call them dot plots. The other thing that we're interested in would be those outliers. Now keep in mind that we already know what outliers are. Outliers are those things that kind of make us go, maybe I need to go back and look at this again, right? We've already talked about this earlier in the semester, but you still can identify outliers in a scatter plot. Where did we identify outliers graphically? Remember? Box plot, right? When they fell outside of the whiskers. So this is, if I have this two variable relationship, I can identify outliers in a scatter plot as well. Okay, let's look at this scatter plot right here. Okay, we won't spend a lot of time on these things, but it's an example. And just to kind of get us talking and just to kind of get an idea of what we're looking at here, we want to be able to describe, using the scatter plot, the direction, positive versus negative, the form, in other words, is it linear or not, the strength of it, so is it strong, moderate, strong, whatever, and then any unusual features. So in this particular scatter plot, we're talking about the cost of women's clothes and the food costs. You can pretty much throw any two variables in a scatter plot. And what we want to know is there a relationship between the two variables? So for this particular one, we would say that there is a positive association, right? Do we agree with that? There's a positive association between the cost of women's clothing and the cost of food. Okay. We would say that it is linear. I would say that it's straight or linear, right? It's all kind of moving in a general linear direction. How would you describe the strength of that? Moderate. Yep. Okay. I don't know. There seems to be an outlier possibly at the end right there, but maybe not. I don't know. It just kind of is the one that's on the end. It's not terribly bad, but it maybe would be something to look at. And because this is a positive relationship, we would say that it appears then that as the cost of women's clothing are increasing, then the cost of food is also increasing. That's all it says. Okay, we don't know much more after that. Let's look at this one here. Average hourly wage. Average hourly wage, right? If we're thinking about direction here, would this be a positive direction or a negative direction? It would be a negative direction. Is it linear or not? No, it's definitely got a curve to it, doesn't it? Okay, all right. How about its strength? Seems very strong to me, right? Because it's really kind of close in right there, all right? And other than that, I don't know that we can say much else, except that what we're looking at is our average hourly wage and the number of hours to earn an iPod. You can tell how old that example is because I don't think anybody has an iPod anymore, right? Okay. What we're suggesting there then is as the average hourly wage increases, what happens to the hours you need to earn an iPod? Well, as this one, if it's a negative relationship, right? As your hourly wage increases, the number of hours it takes to earn the iPod would be decreasing, which would be that inverse relationship, right? Okay, so that would be our negative direction. Okay, I think we get an idea of what's going on here. Just real quickly, if we look at this one, vacation days and the cost of food. Does it look like there's a relationship right there? Not really, right? Okay, so you can see that if you have two quantities, right? If you've got two things that you want to throw in and see if there's a relationship, you can do it with almost anything. Okay, but we can see that that doesn't always mean that there's a relationship. Now, let's talk about the variables that we're used to seeing here. The variables that we're used to in a traditional math class would be our x and our y variables, right? We've said that our x variables are typically the ones that are in the x variables are typically the one along the horizontal axis. Those are the ones that we've considered independent variables, if you think about it in mathematical terms. And our y variable, the vertical axis, would be dependent. Okay, typically we would say that the y variable depends on what the x variable is. Any value you put into for an x value, right? If I had an x value that I put into an equation, I figure out what the value is, and the output would be the y value. That's how come our x is independent, y is dependent. Here, we're sort of rephrasing how we talk about them. In this case, we call the x variable the explanatory or the predictor variable. It's what we're going to use to provide some sort of information or prediction. And the y variable becomes the response variable. Right? It's what we want to predict. So that's a little bit different way for us to be thinking about it. And here I have two examples or three examples, and the answers are already put up there, but we'll kind of go through them anyway. It says, which is the response and which is the explanatory? So in the first bullet you see up there, it says, do baseball teams that score more runs sell more tickets? Do baseball teams that score more runs sell more tickets? So the selling of the tickets, right, is predicting, or we're trying to predict the selling of those tickets, right? If you score more runs, is it going to sell more tickets? Is that the question that's being asked? So that's why, because we're trying to predict if we're going to sell more tickets, that the selling more tickets becomes the response variable and the scoring of the runs becomes the x variable, the predictor. Okay. Do students with a higher SAT score get better grades? Do students with a higher SAT score get better grades? We're trying to predict the grades that are from the students, and we're using those SAT scores to see if that's what's happening. Depending on the question, could be dependent on which one is your predictor and which is your explanatory, right? It depends on what you're trying to ask, because I could certainly see this being flipped. but it depends on the question that you might want to be asking. Okay, and then finally, which can we estimate a person's BMI by measuring their wrist size? So if you measure their wrist size, that's supposed to predict the person's BMI. All right, kind of just some examples that we might be looking at right there. Okay, now we are talking about, we want to use correlation, we want to use scatter plots to determine whether or not there is this correlation between those two variables, the predictor and the explanatory. That's the idea here. Okay, but before we get into the strength and the measure of that, I do want to point something out here. Do these two graphs look the same? These two scatter plots? They look almost identical. What is the differences between them? Okay, and what is that?
One is lower than the other. It looks like it's almost half of what the other
Okay, so the values are lower. Why do you suppose that would be?
one's in centimeters and one's in inches.
All right, so the one on the right would be the metric system, and the one on the left would be the English standard system, right? So they're both talking about height and weight from women. The one on the right is saying that they're going to measure their height in centimeters and their weight in kilograms. The one on the left is we measure their height in inches and their weight in pounds. Okay, does it have an effect though on the relationship? No, it doesn't. And that's the point of what we want to look at here. We want to understand that our correlation that we're fixing to define is unitless. Now, I'm not going to ask you at all to copy down this formula. The only reason I put this formula up here is because I want to talk about what we're fixing to let the technology do for us. Little r, I call it little r, lowercase r, right, is called our correlation coefficient, or just r. It's called our correlation coefficient. We've been using the correlation coefficient. It first showed up for us when we were doing the test for normalcy in chapter 7, but now we're going to define what it is. Okay, so R is defined by taking the sum of the z-scores of your x variable times the z-scores of your y variable and dividing it by the degrees of freedom in essence. Okay, what do we know about z-scores though? Right, z-scores. Are z-scores resistant to outliers? No, right? Z-scores are not resistant to outliers. They're easily influenced by outliers. Remember that? Okay. Remember that z-scores and means and standard deviation are all easily influenced by outliers. So what can we say then about R? Would R, this correlation coefficient that we're defining, also be easily influenced by outliers? Yes, it would be, because it's kind of made up in its definition, right, in its calculation. Okay, so this is how the R score, or how our correlation coefficient is calculated. This is the reason for it. We don't really care about all of that. We just need to know this part right here that I highlighted in yellow. The R, which we define as the correlation coefficient, measures the strength of the relationship of the two variables we're trying to compare. So R becomes a number that we can use to measure how strong of a relationship do I have. So do you remember we were kind of saying, well, although it's subjective, we can see the dots, right? And we can say whether or not something has a strong relationship or a moderate or like no relationship at all. Okay, well, without looking at the dots, you can determine that strength of relationship numerically by looking at the correlation coefficient. And we'll define exactly how that shows up in just a minute. So some assumptions and conditions for our correlation. R, all right, R has to be, or in order for us to use R, I should say, the correlation coefficient is only for linear relationships. So remember how we looked at the fact that we could have other relationships that were nonlinear, that were maybe curved or exponential or something like that. That's we don't use the R to define the strength of that relationship. R, the correlation coefficient, is only used to define the strength and relationship of a linear function, and the two variables that we're comparing in this relationship have to be quantitative. Okay? So we would be graphing a correlation of two quantitative variables. We would also want to see that those points lie in some reasonably straight line. Hence the reason why we're talking about it being kind of linear, okay? And then because it is not resistant, because our correlation coefficient is not resistant, you want to just kind of make sure that there aren't any strong outliers. So let's kind of go back for just a second and let's look at that one picture that we were talking about earlier, cost of women's clothes and the food costs. All right, we already determined that it was somewhat linear in nature. And what we can find is that when we use technology, because any software program out there, that would be your calculators, your graphing calculators, Excel, any statistical package is going to be able to calculate this correlation coefficient. So when we use technology to find it, we'll find that the correlation coefficient R for the relationship here is 0.774. All right, so that's the number that technology gives us. So we know two things off of that number. We know, first of all, that the number came back being positive, which supports our conclusion there that the relationship was positive. Okay, and we're going to see that when we look at our R value, and I'll define this again in just a minute, but what we're going to see is that this R value is going to bounce back and forth between negative and positive 1. Okay, that's it. It just goes back and forth between negative and positive 1. So there's a 0 right there in the middle, right, between negative and positive 1. So the closer my R value is to 1 or negative 1, I have a strong relationship. And the closer my value is to 0, I have no relationship. So it's a way for us to measure that. So because this is 0.774, we would say that it has a somewhat strong positive relationship. Okay. Okay. Now, let's look at this example right here. We'll kind of see how this is done in practice. This says a survey was conducted in the United States and 10 countries in Western Europe to determine the percentage of teenagers who had used marijuana and other drugs. I'll admit, this is an old example that I had found that I thought was interesting. And when I put it on here, I thought it was interesting because at the time that I had added it to my notes and I came across it, there were more states in the United States that were voting on whether or not to legalize marijuana. And so I could see how this question might be a question that people on both sides would be asking. Does marijuana use increase the likelihood of using other drugs? In other words, is marijuana a gateway drug? That would be the question that they're asking, right? And although this is old data, I just heard about this in the news again the other day. And so I would be interested to see an updated version of it, since we have had more states increasing the legality of marijuana use. And I would wonder, had they had an increase in other drug use then? What happened with that? Did it cause it or not, right? Because that keeps coming up in the news. So what they have here is they have the percentage of teenagers who use marijuana and the percentage of teenagers who also use other drugs. Both of those values would be quantitative values, all right? And so they want to know whether or not there's this relationship between marijuana use and other drug use. If they're asking whether or not marijuana would be the gateway drug to other drugs, marijuana becomes the X variable, right? And other drug use becomes the Y variable, right? Okay. So marijuana would be the predictor and the other drug use would be the Y. So if I plot this, that's the first thing you do when you have data. All right, you go in just like we did in other histograms, bar graphs, right? We plot the data and we look at it. So they only had 11 countries that they looked at. But if we're looking at those values here, how would you describe this? Is there a relationship? Does it appear that there's a relationship? Yeah, all right, I would say so. You know, data is not perfect, right? Do we say that this is linear or not? It all looks like it's kind of going in that linear fashion. What about the strength of that relationship? Moderate, I would think so too. Okay, it doesn't look like it lines up exactly, but it does look like it's, you know, not just a bunch of dots thrown on the screen, right? Okay, very good. I would agree with all of those conclusions. Now, what we have here is, and we're going to learn this on Tuesday of next week. What we have here is a technology has shown us. So we put the data, we put the chart up there, right? All of the data from the marijuana use and the other drug use goes into StatCrunch, and we ask it to come up with the scatter plot and the other stuff. So the other stuff that it's giving is this regression, this simple linear regression results. I'll explain to you a little bit later what this means. But what I want you to see is through technology, it gave us the correlation coefficient of 0.934. Right? So remember I said if the correlation, if R is closer to 1 or -1, we have a strong relationship, and the closer it is to 0, we have a weaker relationship or no relationship. All right, 0.934 is indicating it would be a rather strong relationship. I think I would concur with you all that just looking at the 11 data points that are up there, I don't know, it looked kind of moderate to me as well. So understand that modifier that we're using, the strong, moderate, whatever we want to call it, right, is somewhat subjective again, okay? Now, the reason I grabbed my yardstick here is because old school, when I used to do these things, and I don't remember what grade it was, but I do remember, the point of this is you take this data right here and you create an equation. You create an equation that's called the line of best fit, all right? If you remember doing a regression in high school with your calculators, where you would put the data in a calculator, and then you would ask it to come up with an equation that fit the data, that's what this chapter is about, okay? We're focusing on an equation that would be linear. There are many other types of equations that you can find to model data. But what we're looking at here is we come up with this equation. So what I used to have to do is put a ruler on top of this, and then we would measure the distance. We would kind of eyeball it and then come up with an equation based on algebra. Technology gives us the equation now. The reason that we use that is because if I can come up with an equation that models the data, I can go back and look previously how well it was going, right? How well the model would be. And then I can also use that model to predict things in the future. All right, that's the whole reason why we model, is to be able to predict things that happened possibly in the past, as well as prediction in the future. Okay, and again, we'll be coming up with that equation. We'll have technology come up with that equation for us a little bit later, but you can see here that the equation that was given to us falls on this line right here, where it says our other drugs, right, our y variable is going to be equal to this value times, that would be the slope, if you remember what the slope looks like, times our x variable. It's the point, it's the slope-intercept point. Now the conclusion, just based on that information, the conclusion that I can come up with, and nothing more, is simply that because our correlation is 0.934, that indicates there's a strong positive association between marijuana use and other drugs. The tendency is for other drug use to increase as marijuana increases. There's a couple of things about that last sentence. First of all, they're kind of defining for the reader, right, or interpreting, I should say, for the reader, in terms of this context, what it means for there to be that positive association. As marijuana increases, then other drug use increases, right? Whereas other drug use was increasing, marijuana increases as well, right? So they're interpreting that for the reader, which is important, okay? And the other thing that's in there is that wiggle word, right? I call it a wiggle word. The tendency is for. So, we've seen enough statistical statements this semester to see that you never ever say in statistics, I don't believe that I've read, where it says, for sure, if you smoke marijuana, you're gonna use other drugs, right? That's not what it's saying. It just says there's a tendency for it to happen, right? Okay, so that wiggle room shows up in there. Okay, now the properties of correlation. Or the properties of R, something that you probably want to make sure that you are writing down there. Okay. What we have is, you can see that I have 4 graphs up there at the top, and each one of these graphs, the relationship starts to progressively fall apart, and we can kind of see that. The one on the very far left is a perfect positive correlation where R would be equal to 1. We don't live in a perfect world. It's very unlikely you're going to get a correlation that looks like that, but that's what it would look like. Then as we move to the right, we have a strong positive correlation. Notice that the R value there is not only positive, but the value kind of lowered down to 0.8. It's less than 1, but it's still close to 1. And then in the third example there, you still have that linear fashion, right? You have all the dots that are tending to line up in a somewhat linear fashion. That correlation coefficient R is at 0.3. We would describe that as being moderate to weak positive. And then of course you can see the last one over there, which we would say no correlation, because it just, again, looks like a bunch of dots splattered on the screen. No relationship at all. So what we know then is, we know that when R is greater than 0, we have a positive association. When R is less than 0, we have that negative association. And when we have R, we want it to be sandwiched in between negative and positive 1. We also know that R is unitless, but it is not resistant. Remember, R is not resistant to outliers. It's easily influenced for outliers. Although we come up with a different equation, if I were to switch the X and the Y variables, okay, that would give me a different regression equation. It doesn't affect your R value. The R value, the correlation coefficient, is simply measuring that relationship between the 2 variables, okay? So it doesn't really matter if you switch them. It will matter on Tuesday, but it doesn't matter if we're just calculating that R value. Make sure that you understand that your correlation exists between, must be linear in nature. And that it's got to be quantitative variables. And then we've already gone over those other ideas of different adjectives you can use to describe our variable. So what I want you to know out of your properties are that R is between negative and positive 1. When you're close to 1, it's very strong. When you're close to 0, little to no relationship. It's unitless, but not resistant. Okay. Okay. And that, again, that kind of starts to repeat itself. Now, how strong is strong? This is an interesting concept. I had this conversation with my daughter the other day, and I remember, actually last night, and I also remember her talking about it in her other classes. So my daughter has a degree in chemistry, forensic chemistry, but she has 2 degrees. Her other degree is in criminal justice. So she had both the sciences, right, the STEM classes with chemistry and biology, and some physics and stuff like that, but she also had the other classes with criminal justice and those sorts of things. And it was interesting when we were talking about R values and she was going through school and everything, because what they're telling you up here is the description for strong, weak, whatever, right, based on your R value can really depend on your study and maybe even what field you're in. So like an R value of maybe 0.4, which could be considered really strong in kind of like the liberal arts or the social sciences, or like like social work and psychology, criminal justice, she had said, all of those things, that might be a strong relationship in that field. In a STEM field, that relationship of a 0.4 or whatever I just used as an example would be considered really weak. All right, so it just depends on what field you're in, what study you're looking at, to determine what would be considered weak and what would be considered strong. So it's kind of an interesting concept to keep in mind, that it's not some hard and fast rule that says if it's a 9, it's going to be really strong, or if it's a 4, it's going to be weak and we throw it out. Okay, it kind of depends on whatever it is that you're looking at, and that's exactly what this is kind of talking about. Okay. Okay. If we can talk about correlation, that then moves us into causation. Now we come back and we're hitting this one more time. We actually talked about association and causation back when we looked at observational studies and experiments. Do you remember that? Observational studies and experiments. Observational studies were things that showed us whether or not there might be an association between something, but we could never say that just because there was an association that caused it, right? We had to have an experiment to be able to say that something definitively caused something else. So we can say 2 things have an association. We want to be careful in saying that that association is what caused the opposite or the other thing, right? Okay, so that's what we're talking about here too. Remember, we're talking about using some quantitative value to talk about correlation or association. So here I have a scatter plot. You can see the independent variable down there would be the number of storks. The dependent variable on the left would be the human population. All right. And would we say that there is an association there, just based on the scatter plot? Roughly, yeah? I mean, it looks like it's somewhat in a line. Okay, so we might say that there is an association, the positive association. What does that mean in context to this? What does it mean to have a positive association in context to what we're looking at, these variables?
When one goes up, the other goes up.
Okay, put it in terms of this. You're exactly right. When what goes up?
When the number of storks goes up, the human population goes up.
Okay, so this is suggesting that there is an association between storks, right? The increase in storks and the increase in population. The increase in storks and the increase in babies. Do we think that that's right? Do the increase in storks bring more babies? No, they don't, right? You all need to go back to biology class, right? Okay. We can see from the graph we just put up here that what we're saying is that there is an association, right? But one does not cause the other. Okay, just because I can say that there's an association, I can put a graph up here and make an association between any two things I want, right? But that doesn't necessarily mean that one causes the other, right? Does the increase in storks cause the increase in human population? In other words, are the storks bringing more babies? No, right? Okay, so maybe there's something else happening here. there is an association. We can see that there is an association between those storks and the population. Okay, but maybe that's not what's causing it, right? Here, this was a study that was done, and they found that the reverse was actually happening, all right? That storks were nesting on house chimneys, so the increase in population was actually causing the increase in storks. Okay, not more storks bringing more babies. Okay. So we talked about this before. We just kind of want to hit it one more time. We talked about it when we talked about observation and experiments, that you have to be careful about causation, right? Cause. So causation is a possibility, but it doesn't prove something, right? It could be in the reverse. And the other thing to think about is, what could the lurking variables be? Which was another thing that my daughter was pointing out to me last night. In chemistry, for example, she said you can pretty much account for the lurking variables, right? That's why they can have these relationships that have maybe a really high R value and a really strong model for their data. But in the social sciences, let's say, you can't always account for all the lurking variables that are going to be behind the scenes in your study. So that might be the differences between the two. So the lurking variable could be something to take into account here. This is an interesting concept. The number of gray hairs and wrinkles are strongly correlated, but dyeing your hair black does not undo the wrinkles. So in other words, age is the lurking variable that causes both of those things to increase. Okay. All right. And then the final thing that I would point out here, I thought this was an interesting tidbit that came out about the time that I was working on this lesson. And it was an email that we had gotten here at school. So the school has, and I think most universities have, an institutional research department. So like a department that does the statistics for their college. And at the time, Dr. McCowan, who's the president of the college, was going to go on the news for an interview about dual credit, because I think we were expanding the dual credit program here at MCC. And so they ran some numbers, and this was the email that got sent out. These were the bullet points that she was taking as well. Dual credit students retain better than those without. So when we say retain, we talk about staying in school and not dropping out before your completion. So dual credit students retain better than those without. More than 70% of dual credit students return for their second year, compared to less than 50% of those without dual credit. These were the numbers that we were getting at this time. Dual credit students tend to have a higher GPA than those who don't. GPAs of students with dual credits are about a half a point higher than those without. Students who take dual credit tend to graduate faster than those without. For the fall of 2012, first time in college students, almost 30% of those with dual credit graduated in 2 years, compared to only 7% without dual credit. And they didn't include those that just left here and moved on to four-year schools. Dual credit gives students the experience of a college level work while still in high school, and that is an important advantage when they start college. Now, what was interesting to me was they sent the data out to us all in the college, but I loved how he took this last sentence right here and he summarized what he was talking about. This was the head of our statistics institutional research, and he says, note that the first two bullets are not necessarily direct cause and effect. Having every student take dual credit doesn't necessarily mean the result in the outcomes listed. And instead, students who are more likely to do well tend to take dual credit. In other words, he was explicitly describing that one does not cause the other, that there might be an association and there might be a tendency that you can look towards, but you can't definitively say just because you take dual credit, you're going to excel in college. Direct causation. Okay, so that's kind of an example of how it's used in the real world, I would say. All right, let's take a minute, and I want to together, we'll finish off our lesson looking at that paper that you have, your notes that we have right there. We'll just do a couple of these together. So if we're just looking at those two scatter plots right there, we want to know whether or not there is a relationship, and if so, is it positive or negative? What would you say for that scatter plot on the left? So, all right, positive, and you're saying it is a linear relationship. Yeah, I would probably agree. How about the one on the right?
Yeah.
It's not linear. Okay, it's not linear. Very good. All right, let's look at the next graph below that. So here we have a scatter plot for the relation between the median income in a state and their birth rate. Does it look like there's any relationship that you might see there? I don't think so either. It just looks like a bunch of dots up there, right? Okay, I don't think there's a relationship. Do you see an outlier? Where would it be at? Top right corner, right? Okay, so that outlier happens to be the median income and birth rate for the state of Utah. Okay. Now, when you have that outlier, remember, when you have an outlier, it's just supposed to make you go, why is this? Is it a data entry? Because it'd be really easy to reverse the numbers when you're putting them in, right? Something like that, or maybe you put an extra value in there. Data entry error would be it, okay? Or is it truly something that is actual data? So if that point right there represents the information from Utah, do you think it's a data entry or do you think it's real, and why? What is Utah known for? It's just a fact. What is Utah known for? Do they have a high population of Mormons in their state? Okay, so there's nothing wrong with saying that perhaps then the high birth rate has to do with a religious belief, right? Yeah. Okay. Could you not say the same thing? Maybe if you maybe there's other religious beliefs that have a high birth rate. Okay, that's all they're saying. So it just makes you though go back and go, okay, well maybe this is why. I think polygamy is legal there as well. So a lot of things could lead to a high birth rate in Utah, perhaps. Now, looking at the next question or the next part of that, it says that the correlation coefficient R for this particular scatter plot or this particular set of data is negative 0.07. So how does that support our conclusion that there's no relationship? If you couldn't look at the scatter plot and only looked at the correlation coefficient, found out that correlation is negative 0.07, what would you conclude and why?
There's no strong correlation because it's closer to 0.
Exactly, that's all they're asking. Right? There's not a strong, or there's no relationship, which is what we concluded just visually looking at the graph, but it supports that conclusion because that correlation coefficient R is so close to 0. And it can be positive or negative, that doesn't matter. It's the fact that it's close to 0 that was important. Okay, and the last thing that I want to do together, let's turn over to the back. Look at this question number 5. We want to see what's wrong with this statement. So I'm telling you right now that there's something wrong with the statement, okay? We have concluded that a high correlation exists between the gender of drivers and the rates of automobile accidents. problem with that. So if we're talking about a correlation, right, and we're thinking of this in terms of what we're talking about today, what type of variables are we looking at there? What are the two variables?
Gender, number of accidents.
Okay, gender and the number of accidents. What type of variable is gender?
It's qualitative.
It's qualitative. What type of variable are the accidents?
Quantitative.
So do we have a problem? Why? Why do we have a problem?
It must be quantitative.
They have to be quantitative, right? Isn't that what we said? The two variables have to be quantitative for us to be able to determine that correlation between them, right? That's what we're talking about, okay? That high correlation exists. So just like I said before, I could have numeric, I could count up, data for car accidents for women and for men and graph it, but that doesn't mean that there's a correlation coefficient for it because it's not linear and it's not, because it's not two quantitative variables. Okay, maybe a better way to be able to state this goes back to when we did our observation versus experiment chapter. We talked about observational studies allow us to compare things that are not, that is when we can compare quantitative and qualitative things to each other, okay? Which would be this type of example. Instead, we would have to say something more like gender is associated with the rate of automobile accidents, okay? You're just going to make that association, not the fact that it's a correlation. That's kind of the difference that we're looking at right there. All right. Are there any questions